Let's review the basic principles for camera setup for a machine vision application. Everything begins by deciding the minimum feature size and associated spatial resolution, and from there you can determine the required camera to object distance and then also determine the available field of view. Let's consider a simple machine vision application. I'm looking at a collection of coins, and I'd like to determine the total value of the coins based on the measured diameter of each coin. As you look at the image, of course, we have a range of sizes. The dime and the penny are the most similar, and these are the ones that guide our choice for minimum feature size. These two most similar coins have a difference in diameter of 1.14 millimeters. I'm going to make the decision to allocate 10 pixels to this difference, and that should be enough to be able to differentiate those two diameters. Minimum feature size, 1.14 millimeters. Number of pixels to allocate is 10. That means the required image spatial resolution is the ratio of those two numbers. That gives 0.114 millimeters per pixel. Now, we need to determine what camera distance is required to obtain that spatial resolution, and then also what will be the field of view at that camera distance. We have a basic trade-off here where better image spatial resolution, which makes it easier to differentiate the penny and the dime, means we can't see as many coins. So we need to establish a balance between resolution and field of view. Now in my setup, I have a Microsoft LifeCam Cinema webcam attached to a tabletop copy stand, and this is the RPS 9-inch by 12-inch model. The webcam is looking at the object plane, and we can summarize this setup using the Pinhole camera model. This is kind of an idealized model. It's based on a projection center in the middle, essentially the lens. We have our image sensor on the top, and then down here at the bottom we have the object plane. Now the Pinhole camera model allows us to work with the object plane spatial resolution, the image sensor spatial resolution, I'll call that RS prime, and then we have the distance from the projection center down to the object, the distance from the projection center up to the image sensor, and it should point out that both those values are unknown. The projection center, however, is not the only way to measure distance from the object. We can pick some reference feature on the camera body itself down to the object plane, and I'm going to call that distance D. Typically that value is going to be somewhere from the object plane to the middle of the camera body, and there's some difference, small d, between that point and the projection center. Here's another webcam model. This is the LifeCam Studio. I point this one out because in particular a nice reference mark is that join between the black and the silver part of the body. So you can have your reference mark in different places depending on your camera. Now, by the geometry of similar triangles, we can say that the ratio of these two spatial resolutions in both the object and image planes is equal to the ratio of these two distances. That is, the two distances from the projection center. Now, the distance from the projection center down to the object plane is also based on knowledge of that external reference mark distance. So let's go ahead and solve for that distance, capital D, and we have this simple equation. Now this ratio is composed of two values for which we do not have any information. I'm just going to represent that ratio by the so-called camera constant K. Now looking at this basic equation, we see that little d, that's the distance from the external reference to the projection center. Capital D is the distance from the reference mark down to the object plane. Based on looking at the units here, we see that the units of our camera constant is pixels. Now, as I say, the camera constant is unknown. Also, this little d distance that's internal to the camera is also unknown. How do we find these values? Well, we can measure the camera distance and the spatial resolution at 2 or more distances. We either solve a pair of simultaneous equations or find a best fit regression line. Here's an example. I took some measurements at 2 different camera distances, D1 and D2. I took an image of a ruler. I found the millimeter marks in 2 different places on the ruler and the associated pixel values at these 2 locations, and came up with 0.163 millimeters per pixel for the first measurement. Second measurement, where the camera is closer, came up with a different value, 0.0641 millimeters per pixel. Now with 2 equations, you can solve that pair of equations simultaneously and you come up with the camera constant and that distance from the projection center to the reference mark. In this particular case, the value is negative because my reference mark is actually the very front edge of the webcam, and that's in front of the projection center. If we go the other direction, then we would end up with a positive value. Now, the field of view is the total distance that can be imaged in the object plane. Now, looking at the object spatial resolution times the number of pixels that are available in our camera, that is the number of sensor pixels, and let's differentiate between horizontal direction, n sub h, and vertical direction, n sub v. And let me come back and call that field of view in the horizontal direction and field of view in the vertical direction. Those 2 values, n sub h and n sub v, are properties of the camera. If we assume that we've got square pixels, which is generally the case, then we use the spatial resolution for each. Well, let's finish up by taking a look at a plot of camera distance and field of view as a function of spatial resolution. This is based on knowledge of the camera resolution, 1280 by 720, 2 or more spatial resolution measurements, and from there you can calculate the camera constant and that little d distance. Here I have the 2 values, or 2 measurements that I showed you earlier. That's based on the slope function in Excel, and this is based on the intercept function to get at little d. Here I'm using the equations that I developed earlier to calculate the camera distance and field of view values. Just a reminder, the coins application requires 0.114 millimeters per pixel for spatial resolution. And let's project that line up, and that intersection point then tells us the field of view limits as well as the required camera distance. For example, we see that the required camera distance is approximately 100 millimeters, and the field of view is approximately 150 millimeters by 85 millimeters. Now I'll finish up by showing you how well this worked out. I'm using NI Vision Assistant for this purpose. I've already adjusted my camera height, capital D, value to 100 millimeters, taken an image of this centimeter ruler. The small marks are in millimeters. Look at the pixel coordinates there, 597 to 606, as I span 1 millimeter. And that means the spatial resolution is 0.11 millimeters per pixel. You could also try repeating this for a different millimeter value. I'll also try this out for 10 millimeter span. Looking at those 2 coordinates again, taking the difference, come up with 0.112 millimeters per pixel. That's an error of minus 1.8% compared to the target value of 0.114 millimeters per pixel. So it looks like the calculated distance d worked out nicely based on the equations.